We will now discuss a very important notion, namely that of convolution. We will first discuss it for functions and later extend it to classes of distributions. Okay. So, let us take f and g Borel measurable functions on Rn, and then you have that xy going to x, y, and xy going to x minus y are continuous, and therefore if you compose, then you have f of x minus y gy is a Borel measurable function. Okay. Now if you look at if f and g are integrable, so if you combine compose continuous and Borel measurable, you will get Borel measurable. So if f and g are in addition integrable, then Lebesgue and Borel measure coincide on Borel sets, and therefore you can apply Fubinis theorem. Therefore you have that integral. So if you write f of x y equal to this, then if you look at integral mod f of x y over Rn cross Rn dx dy. Now this is equal to integral over Rn mod gy integral over Rn mod f of x minus y dx and then dy. Since everything is non-negative, you can do this. And now Lebesgue measure is translation invariant, and therefore this will give you equal to norm f1 in Rn, and then that leaves you only with mod gy, and therefore that will give you norm g1 as well. Okay. So this means by Fubinis theorem again, you have that the x section, namely f star x of xy equals f of y f of x minus y gy is in L1 of Rn, and so we can and so h of x equal to integral f of x minus y gy dy over Rn is well defined. Now if f and g are Lebesgue integrable, then f and g are almost everywhere equal to Borel measurable functions, and therefore since integration does not depend, when you have functions almost everywhere the integration is the same, and therefore hx well defined again. Okay. And we also have that norm of h in L1 of Rn is less than or equal to norm f in L1 times norm g in L1 by the preceding calculations. Okay. So therefore you have this is well defined. Now this is called the convolution. So definition. So henceforth we won't make a fuss of Borel and Lebesgue and so on. So we will say fg in L1 of Rn, then the function h of x equals f of x minus y gy integral over Rn dy is called the convolution of f and g and is denoted by f star g. Okay, and we have that f star g belongs to L1 of Rn, and we saw norm of f star g in L1 is less than or equal to norm f in L1, norm g in L1. Okay, so this norm 1 is nothing but the L1 norm in Rn. Okay, so since the convolution is well defined and you produce again an L1 function, so we can define f star g star h. Now this h, so if f g h are in L1 of Rn, so this h is not to be confused with this h here, which is a temporary notation which I used. So you can define f star g star h because this L1, this also L1, and f star g star h are defined. So now we have the following theorem. The convolution is a commutative and associative binary operation on L1 of R. So this is just again repeated use of Fubini and the fact that we have translation invariance of the Lebesgue measure. So f star g of x is equal to integral Rn, I will write with respect to y. So just to tell you which is the variable of integration. So fy gy dy. So I am going to make a change of variable. So this becomes Rn of z. So I am going to put f x minus y equals z. So this becomes f of z times g of x minus z, and then by the change of variable further, this will just give you dz, and that is in fact equal to g star f of x. So we have just used a change of variable, a linear change of variable. Okay. Okay. So now let us take three functions f star g star h evaluated at x. So this will be integral Rn y of f star g x minus y and h of y dy. So that will be equal to integral Rn y times integral Rn z of f of x minus y minus z gz dz and then hy, sorry, dz and dy. So now again I am going to make a change of variable and use Fubini repeatedly. So this will be Rn of w of f of x minus w. So I am putting y minus z equal to w, and that's equal okay, integral Rn y of g of w minus y, okay, hy dy dw. Now what is inside is nothing but integral Rn w So this should be Rx minus W. Okay. So y minus z I put y plus z equal to W. Okay. So f of x minus W. So y plus z. So z will be W minus y, correct. Okay, so y plus z equals W. So this will be integral Rn of W f of x minus W times g star h of W dW. And that's equal to f star g star h of x, and therefore this is a associative operation. Okay, so now we can extend this definition. Okay, so the next theorem, let 1 less than p less than infinity, let f belong to L1 of Rn and g in Lp of R. Then f star g is well defined. Further, f star g will belong to Lp of Rn, and you have norm of f star g in Lp is less than or equal to norm f in L1 and norm g in Lp. Okay, so proof. So if p equals 1, which we have excluded here, we have already seen f and g are both in L1, then f star g is in L1, f is norm f1, norm g1. That is what we already proved. Now we are going to extend this result. So when p is strictly bigger than 1 but less than infinity. Okay, so let p dash be the conjugate exponent of p. That means 1 by p plus 1 by p dash equal to 1. So you have 1 less than p dash less than infinity as well. Okay. So then you take h in Lp dash Rn. Now you look at the map xy going to f of x minus y, gy, hx. So this is measurable and by Helder's inequality, so measurable. So by Helder, and translation invariance of Lebesgue measure, we have integral Rn x integral Rn y of mod f of x minus y gy hx dx dy dx. So this is equal to integral Rnx. So everything is positive. So I can need not worry about any integrability, etc. I can use Fubinis theorem straight away. Integral Rny f of x minus y mod gy dy dx. Now that is equal to integral Rnx mod hx integral Rnw. Again I am making a change of variable of mod x minus y I am going to put as w. So I get mod f of w g of x minus w dw dx. Now I apply Fubinis theorem. I bring out the w. So this is equal to integral Rn of w mod f of w, you can keep out, and now you write Rn of x mod hx mod g x minus w. dx and dw. Now, what do you have? F is in L1, G is in LP, H is in LP dash, they are conjugate coefficients. So, by the Rees representation theorem, so this is less than or equal to, and you have the translation invariance of the Lebesgue measure. So, you have norm H in LP dash of Rn, norm G into LP LP of Rn. So, I am bringing out, so this, because of W is fixed, this is just translation by W, and therefore this has the same norm as the norm in LP. So, norm G in LP, norm H in LP dash, that is Helder inequality, and if those come out, remaining is just norm F in L1. So, what is left is nothing but the integral of F1. So, this is into norm F in L1, okay, and that of course everything is finite. So, since all this is finite, so by Fubinis theorem, when you have everything for the modulus is finite, so the integral over Rny hx f of x minus y gy dy exists for almost every x, okay. So, now you choose H in LP dash Rn such that Hx is not equal to 0 for all x. So, example, you can take Hx equals e power minus mod x square. Now, this belongs to all LP spaces, and this is strictly positive for all x, and therefore, you can take like that. So, Hx is not is a constant as far as this integral is concerned, and therefore, it comes out. So, you can divide by it, and therefore, so this implies that integral f of x minus y gy dy over R and y exists, okay. And further we have shown that H going to, so and therefore f star g is defined. So therefore we can write equal to f star g of x is well defined. So, further we have shown that H going to Rn f star g times H dx is a continuous linear functional on LP dash Rn by this inequality which is here, and therefore with norm with mod integral over Rn f star g h dx less than or equal to norm h p dash norm f 1 norm g in p. So, what does this mean? By the Rees representation theorem, we have that f star g must belong to the dual of LP dash, which is LP of Rn, and the norm of f star g in LP is less than or equal to norm f1 norm gp. So, that completely proves this theorem. Okay. So, remark. So, same we already proved this for, so we already showed this, saw this for p equals 1, okay, that is one thing. And then these are particular cases of Young's inequality. What is Young's inequality? 1 less than or equal to PQR less than infinity. So, you have 1 by P plus 1 by Q equals 1 plus 1 by R, such that. Okay. Then if F is in LP of Rn, G is in LQ of Rn, then you have that F star G belongs to LR of Rn, and norm F star G in LR is less than or equal to norm F in LP, norm G in LQ. So, okay, so this is a particular case of this. Okay. So, now we can go further. So, F and G are continuous on Rn, and one of them has compact support. Then also F star G of x equals integral over Rn f of x minus y gy dy is well defined. Okay. So, now and you have commutativity, okay, and if F1 Fn are continuous on Rn, and all but at most one of them has compact support, then we can define F1 star Fn by doing 2 at a time. So, you can take F1 star F2, then you can take star F3, star F4, or you can do it in many ways. It does not matter how you are going to pair them. So, the pairing is unimportant, the order is unimportant, because the of every convolution which we write, one of them will have compact support, as the following result shows. So, we well defined, since every pair will have at least one member of compact support, as the following result shows. So, theorem. So, Fg continuous real valued functions on Rn, and one of them has compact support. Then F star G is well defined, that is no, we need not, we have already seen this, and support of F star G is contained in the support of F plus support of G. okay, where you know if A and B are subsets of Rn, then you have A plus B is set of all x plus y such that x belongs to A, y belongs to B. Okay, so these are the algebraic sum of two sets. Okay, set of all x plus y, x in A, y in B. So in particular, if both f and g have compact support, then f star g also has compact support. Okay. So proof. So let A equal to support of f, B equals support of g, and without loss of generality assume B compact, because it does not matter f star g is g star f, so you can always assume that this compact. Then A plus B is closed. This is very important. So if you have two closed sets, the sum need not be closed. You try this exercise even in R2, try to for instance you take the y axis and you take the rectangular hyperbola xy equal to 1 and then try to show that x plus y, A plus B is not closed, even though A and B are closed. Okay, so if one of them is compact, then the sum is closed, and from the argument which you are going to give, it will be shown that if both of them are compact, then the sum is also compact. So support of f plus support of g is compact, and therefore support of f star g, which is a closed subset of a compact set, will also be compact, and therefore that will prove the second part of the theorem. So it is enough to show that A plus B is closed and that support of f star g is contained in A plus B. Okay, so we want to show A plus B is closed, so let xn plus yn belong to A plus B. So that means xn is in A, yn is in B, and let us say this converges to some z in R, okay, in Rn. So B is compact, so there exists a subsequence yn k which converges to y, and because it is compact set and therefore it is closed, therefore y and k will converge to y. So this implies that x and k converges to z minus y, call it x, say, and since x and k is, x will belong to A since A is closed. Okay. So this implies that z equals x plus y, which belongs to A plus B. So this implies that A plus B is closed. So if A be compact, this implies that A plus B is compact by the same argument, because both x and y, xn and yn will both have convergent subsequences, and therefore xn plus yn that will have a convergent subsequence, and therefore that A plus B is compact. Okay, so this establishes game. So now if you look at the integral f of x minus y gy dy, so this is f star g of x. This integral is over Rn. It is enough to consider this integral over B, where B equal to support of g, remember, because outside B g is 0, so this integral nothing will get contributed, and therefore this is equal to B. Now if you want f star g x to be not 0, then this implies that x minus y belongs to A, which is equal to support of F for y in a set of positive measure, a subset of positive measure of B. So, only if this x minus y is in the support of F, and it is not enough if it happens at one point, it must happen for many points, so that you have a positive subset of positive measure in B such that this both of them are non-zero, and then you have that the integral will be non-zero. Okay. So, this implies that x itself belongs to A plus B, because x minus y belongs to A. So, where y is in B, so x belongs to A plus B, and consequently set of all x such that f star g of x not equal to 0 is a subset of A plus B, and therefore, if you take its closure, that is equal to the support of f star g, and that will also be contained A plus B, because A plus B is closed. Okay. So, now finally, if remark, if F is continuous with compact support, and G locally integrable on Rn, then also f star G is well defined. And in fact, you have the same support of f star G is contained in support of F and support of G. Okay. So, this is the starting point of very interesting property of convolutions, which gives you really the power of this operation, and we will see that next time.